Swayam Prabha. Digital India. Educated India.
Because we are going to look at IoT systems which are embedded in nature. So I'll talk to you for a little less than an hour about what an embedded system is and how IoT is like an embedded system and also has additional features. So we begin with a small question for all of you. You can think to the answer about yourself. So the question is, can you give examples of what you think is an embedded system or a software? Think in your mind about what would be an example of an embedded system or an embedded software. Just to get you started, will the software that we use to access WhatsApp on our phone an embedded software? Is the software that we use to access, let's say, Citibank online, is it an embedded software? Is Gmail an embedded software? What is an embedded system or a software? So once you have answers to them, here is the definition. So Gmail is not an embedded software. WhatsApp is not an embedded software or a system. So what is an embedded system? So embedded system is a computer system. That's why we are looking at it, which means it has a processor, it has memory, it has input, output, peripheral devices. That is, I can plug in devices, read inputs from them. I can plug out devices or send data out through the devices that are plugged in as outputs, like a USB port, like a sound jack, and so on. Then it also performs a dedicated function within a larger mechanical or an electronic system. So the word embedded comes because it is embedded as a part of a complete device, often including other components, which can be electrical, electronic, or mechanical in nature. Embedded system typically controls physical operations of a machine that it is embedded as a part of. So it has real time computing constraints. So, what would be an example of an embedded system that fits into the definition that we see here? We all are familiar with the voting process that happens in our country and several other countries. Electronic voting machines are boxes that look like these, which are carried around to remote places to collect citizens casting their votes in the various elections that happen in our country. So, an electronic voting machine is a classical example of how an embedded system looks like. It has assembly, it has a processor where you can do computing, it has sensors, it has some kind of display where different symbols of the parties that are standing for elections are provided. Then it has buttons where you can provide inputs in view of your votes. And then inside, in the processor and in the assembly, it has a counting logic where it has logic that is embedded into it or a program that is embedded into it that is capable of counting votes for various parties. Data can be fed into the electronic machine by pressing buttons like votes, and data can be read from it through various ports. So, you see this assembly down here where my mouse is pointing to, that represents the processor and other entities. There are several different ports that are available to read data. And of course, I can connect this to a nice display system through one of the ports where votes of different categories can be cast based on the party symbols that are displayed to the people who are casting the vote. This is just one simple example. There are numerous other examples of embedded systems that we who use technology use in our everyday lives. There are network routers, which we use. These were routers that route our internet network, our telephone networks, telecommunication switches. As you walk across the road, you see so many of them. Programmable logic controllers, which are extensively used in industries to do process control, several medical equipments, all of them are examples of embedded systems. So now let's go back to the previous slide and look at the definition once again. It'll become clearer to you now that we've seen a few examples. So it's a computer system. It has a processor, it has memory, It has inputs and outputs like all other computers do, and it performs a dedicated function, that is, as a part of a larger mechanical or an electrical unit. You might have heard of one more term which you encounter often when you look at embedded systems. That is what is called a cyber physical system. You would have heard this term quite often. So let's see what a cyber physical system is. It is abbreviated as CPS, short form for cyber physical system. What is it? That's also like an embedded system, but it has additional features, additional functionalities. It's a computer system in which a mechanism is controlled and monitored by computer based algorithms. So it's meant to do some monitoring, monitor certain parameters, read certain values, do something. And as a result of that monitoring, it is also meant to provide certain control. So, in order to do the monitoring and in order to provide control, these cyber physical systems run are traditional algorithms that aid in monitoring and control. Compare it to something like a good old small scale embedded systems like a electronic voting machine. It may not run any sophisticated algorithms, it may not do monitoring, it may not do control. It does computation in terms of elementary processing, but it cannot run very sophisticated algorithms. It cannot monitor, receive a lot of information, and provide control functionality. So in cyber physical systems also, they are embedded. So there are lots of physical components, there are lots of software components. They are intertwined, connected with each other. They can operate on different spatial scales, temporal scales. They exhibit multiple distinct behavioral modalities. They interact with each other in a way that changes the context or the environment that is operating around the cyber physical system. Cyber physical systems, usually, several other engineering disciplines also talk about it: cybernetics, mechatronics, design science, process science, all of them deal with cyber physical systems. What would be a simple example of a cyber physical system? Here is a cyber physical system: UAV, or an unmanned aerial vehicle. We all have heard of them, they are very popular these days. This is an example of a cyber physical system. This particular image that you see on the right hand side of this slide represents a Star Mac quad rotor aircraft that was developed by a particular company in collaboration with a particular university. Next few slides down the line, I'll play for you a small video that explains how this quad rotor aircraft works. This is a classical example of a cyber physical system. It has a lot of modeling in it. It deploys a lot of control algorithms, flight dynamics, multi vehicle interaction, takeoff, cruise, landing as different modes. It has several sensors, several actuators. They can talk to the real physical world through interfaces. It also has memory. It also has computing power, processor, deploys a real time operating system for scheduling and other things. Then we also want the cyber physical system to, I mean, it runs a lot of code, it exhibits behavior, so it has to be safe. So we subject such a cyber physical system to a lot of testing and verification, which we bundle together and call it as analysis, where we specify and also test and verify what safe behavior of such a system is. Security, privacy, lots of other things come into picture here. Of course, in electronic voting machines, also those things are important. But here it becomes a lot more complex than what you can imagine. So, this is a classical example of what we call as a cyber physical system. In this lecture, we will learn a little bit more about modeling, design, and analysis of embedded systems and cyber physical systems. And later, throughout the series of lectures, you will see how to apply them specifically in the context of IoT. So now let's come to IoT, which is going to be the topic of this summer school. So IoT, abbreviation for Internet of Things. So what is it? The word things is the most important aspect of IoT. What are things? Things are a lot of physical objects that have capabilities to talk to each other by using the internet. So, an IoT system describes a network of physical objects, which we call as things, that are embedded with sensors to read data from. They have software to run and infer something about the data. They also deploy a lot of other technologies to be able to connect with other things and exchange data with other things. But the technologies that they deploy predominantly use some kind of protocol related to the internet for communication, and that's why they are called Internet of Things. Contrast it with electronic voting machine, which may not be connected to the internet to read data and to exchange data with the EVM. You will have to connect the electronic voting machine manually through a port. But in an Internet of Things system or an application, there could be several devices, and almost all the devices that are present are capable of exchanging data, that is, sending and receiving data by using some kind of internet protocol or the other. So that's why the term Internet of Things. Traditional fields of embedded systems, which includes wireless sensor networks, control systems, home and building automation, all of them now contribute to enabling IoT. Application areas of IoT are numerous. We have several consumer applications. Most of you might have heard of Amazon's Alexa, Apple's Siri Assistant, Google Assistant, all these devices that are meant to provide us assisted living, smart homes. They are extensively used in healthcare applications, for monitoring senior citizens who live by their own, for sending data to the hospitals, for connecting senior citizens to their doctors and nurses. IoT applications are also extensively used in manufacturing, agriculture, monitoring of environment, farming, military, and so on. So they are very popular. We will see lots of lectures on IoT. The school is about that. So now that we've seen three categories of systems, embedded, cyber physical, and IoT, I hope all of you got an idea of what each of them are. So let's spend a couple of minutes trying to think about, can I enumerate differences between what I call a traditional embedded system versus a cyber physical system versus an IoT application? What would be the similarities in these three categories of embedded systems? What would be the differences that we saw in these three categories of embedded systems? It helps to recollect the examples that we saw. We saw an electronic voting machine as a classical example of an embedded system, an unmanned aerial vehicle as a classical example of a cyber physical system. I didn't give you an example of IoT, but you will get plenty of opportunities to see examples of IoT systems. So I'll pause for a few seconds to let you all think about what would be the differences. And in the next slide, I will show you the differences. So here is what I have attempted to list. Let's compare and see how good it, like an electronic voting machine, a telecommunication router. Obviously, you can communicate with them through exchange of data, but their functionality exists as a standalone device. They are designed to do specific tasks that involve core computation logic. If you take the EVM example once again, its task is to receive votes in different categories and to aid the user or the election commission officials to count votes in different categories. It has a very specific task. Its emphasis is heavily on the physical device. It may or may not have a user interface. Cyber physical system is meant to monitor and provide control by as an embedded system. It is designed for transdisciplinary applications. Like, for example, if I take the unmanned aerial vehicle, its goal could be several different things to accomplish a particular mission, let's say 2 hours or half an hour of a flight mapping a particular terrain. In that process, it has to fly in such a way that it avoids obstacles, it has to record data, it has to manage changing weather conditions, several different things. It's designed for transdisciplinary applications. In a cyber physical system, the emphasis is on the intense link between the physical device and the computation. Let's look at IoT. IoT shares the same basic architecture as that of a cyber physical system, no doubt about it. Communication is extensively using internet. By internet, I mean one of the internet protocols down the communication stack. IoT, because it has internet, it also can use extensive cloud computing technologies. So it gets access to a lot of computation power, which a good old embedded system or a cyber physical system may not have. Because an IoT application has a lot of access to computation power, it can run image processing algorithms, signal processing algorithms, several different complex machine learning algorithms, analytics, and so on. So I hope the differences are clear. So why are we studying embedded systems? They better be important for us, right? So Gartner, one of the world's leading technology predicting companies, comes up with what they call a hype cycle. Hype cycle talks about the different trends that happen in a particular area and say which is here to stay and which is not going to stay. I'm sorry if the text is not fully readable, but I hope you can see the hype cycle. So, this is Gartner's hype cycle for embedded software and systems for the year 2020. So, there are these dots that you see: white dots, light blue dots, dark blue dots, yellow triangles, and red circles. If you see, the thing is filled with white dots, blue dots, and dark blue dots. There are very few, exactly one, in fact, yellow triangle, and exactly one red. If you read into it, what it says is that edge computing as a technology is going to stay, device to device communication as a technology is going to stay. There are going to be cool technologies like digital twins, so on and so forth. Several different technologies for embedded systems are here to stay and mature in the next few years. So let's go back to understanding cyber physical systems. As I told you, the focus of this lecture is to understand embedded and cyber physical systems before we move on to IoT. So, this is a cyber physical system, as an example which I gave, represents the star marked quadrotor aircraft. Here is a YouTube video that I would like to play for you. It takes a minute to play. Please bear with me as I change my screen and play the YouTube video. It'll tell you how the quadrotor functions.
Hey everybody, right now, IIT is having a huge sale on their online courses, Learning That One Skill.
This video presents StarMac, the Stanford testbed of autonomous rotorcraft for multi-agent control. The testbed is comprised of 6 quadrotor helicopters, 2 of which are shown here doing autonomous hover using GPS. Experimental applications for this testbed range from decentralized collision avoidance to autonomous search and rescue with a team of aircraft to studying the interactions between humans and autonomous systems. This aircraft design has evolved from many flight tests. The sensor suite for every vehicle includes a GPS unit to sense the position, an ultrasonic major to sense the distance to the ground, and an inertial measurement unit to sense the acceleration and rotation of the vehicle. Additional sensors that can currently be carried in order to perceive the environment include cameras with both binocular and stereo vision, LiDAR range detectors, and avalanche rescue beacon receivers. The vehicles are controlled in real time using a microprocessor to control the highway dynamics and using a high-level control computer to perform optimizations. So this part of the video talks about the number of sensors and the processor and the controller that's present in this quadrotor aircraft. See the variety of sensors, the microprocessors, and the computer. All of it is being carried by the UAV itself. The quadrotor is controlled by varying the relative speed of the motors. For instance, the roll torque is controlled by decreasing the speed of the left rotor and increasing the speed of the right rotor. Yaw is controlled by varying the relative speed of counter-rotating rotors. Vehicle position is controlled by varying the total thrust and vehicle orientation. So that was theory, but when we tried to use the control system design, we found out that there were aerodynamic effects that we weren't accounting for. By modeling these aerodynamic effects, we designed controllers that project these disturbances. The resulting control system design uses feedback on angular acceleration and linear acceleration. As you can see, it's very capable of projecting disturbances. Please observe the dynamics that goes into the design of this quadrotor. It is capable of resisting
and avoiding obstacles.
Vehicles would perform obstacle avoidance experiments, where the vehicles were required to fly around the boxes and not over them. During this test, the aircraft inadvertently blundered into a box, demonstrating the safety and robustness of the aircraft design. Here, an experiment using tunnel milk is shown. The aircraft must navigate from the right side of the field to the left side of the field. To solve this obstacle avoidance problem, the tunnel milk first finds the shortest path to the goal. Then it forms a tunnel around this path and formulates a mixed integer linear program to fly the vehicle through this path under dynamic constraints optimally.
Please note the complex set of algorithms that they're talking about. It does obstacle avoidance. It uses mixed integer linear programming. It has algorithms to find the shortest paths and so on. Yeah, I hope that gave you an idea of what it was to be a cyber physical system. Continuing on with our lecture, if we study a little more about what went into the design of StarMac, this is what it looks like. You can see the amount of sensors. There's a LiDAR sensor, there's inertial measurement unit, there is GPS, there is a camera, there are range sensors. These are the ports with which they communicate with. There are several processors, there is a PC, there are also Wi-Fi ports, and there is a transceiver beacon and a few other things. So this is the architecture that we have about the StarMark quadropter, thanks to the excellent book on embedded systems by Lee and Sashia, from which this has been taken. So let's look at a little more about what goes on abstractly into the modeling, design, and analysis of embedded systems. It's a very iterative process. It doesn't flow from modeling to design to analysis. They happen together, one after the other. They lead to one another, and one aids in the other. Modeling. What does modeling have? Modeling is the process of gaining a deeper understanding of a system through mathematical models, equations, and simulation models that imitate the system as if it was working in reality. What would happen? In short, models specify what a system does. Design. What is design? We all know that when we do design, we are thinking about what are the artifacts that I'm going to create, what is going to talk to what are all the components, what are all the connectors, what are all the algorithms that I'm going to run based on what I want to achieve, and so on. So, in short, it specifies how a system does what it is supposed to do. In addition to that, design also involves, you cannot just deploy brute force algorithms to do what you want to do. You better deploy the best known algorithm to the capabilities that can be afforded by the processor and the computation available in order to design. So, design also involves a lot of optimization, followed by analysis. An important part of developing any system is also to test and verify that the system does what it's supposed to do. All the more for embedded systems because a majority of them are safety critical in nature. So, analysis is the process of gaining a deeper understanding of a system through dissection. That is, I test a system, I verify a system. In this process, I could end up demonstrating an error that tells you why a particular functionality fails, in which case I have plenty of scope to rectify it by changing the design or models then and there. I could also give you a proof or an illustration of the fact that the system works correctly. So these are the steps that go into development at a broad level of an embedded system. So when it comes to modeling, how do you view a cyber physical system? To start with, I view it from a very abstract point of view. I keep repeating this loop when I do modeling. Please remember, cyber physical system is intertwined with algorithms and other entities running on a processor along with the data that is read from the sensors. So there are physical components, which are given here down below, which form a very important part of a cyber physical system. The physical components have to exchange data with each other, and that data is done through a network. And along the way, there is a lot of computation that happens. There is a lot of computation that happens while reading data from the physical components, while sending back data to the physical components also. And all the interaction and the results of the computation are exchanged through a reliable network. So, data, what are the physical components? Data is read from sensors, from actuators, which constitute the physical components. Some communication network, as I told you, is used to read and write data to and from the physical components. Computation represents the main functionality of what the cyber physical system is supposed to do. It's supposed to accomplish flight. It's supposed to avoid obstacles. It's supposed to avoid collision. It is not only supposed to accomplish flight, it's supposed to take the shortest path to the desired mission. There could be several goals that a particular system needs to accomplish. And I write a lot of algorithms, a lot of logic to be able to accomplish that goal. So that what constitutes computation. And this process keeps repeating. There could also be a lot of service routines. Like, for example, you might have something that logs routine data that is collected by a cyber physical system. In the unforeseen event of a fault occurring, you can analyze the data to see if it works fine or not. So, even with the abstract view, there are already a lot of problems that we can see. When I talk about physical components, they are, after all, physical components. They involve a lot of hardware, mechanical parts, electrical parts. So, there is a risk of failure of these parts. There is also a lot of noise that can come in the data that they measure. You could end up doing imperfect actuation while controlling a particular physical components. How reliable are the values that I read from the physical components? So many issues exist. When it comes to the communication network, is the network reliable? Are there packet losses? How much is the delay that messages can come in a network? Do I know all the delays? Do I know a bound on the delay? If there is a lot of traffic in the network, what happens to the data that is sent across? So many issues to deal with. When it comes to computation, there is a whole host of functionalities to be performed, and they all have to be performed in sync with each other. So, in the processor, there are several parallel concurrent threads that run to accomplish all these functionalities. And there could be interrupts. The presence of several threads and interrupts give rise to non determinism. The actual physical laws are something very complex. When we implement them in software while implementing a cyber physical system, we actually come up with an abstraction or a model of the physical law and implement that. So these abstractions could cause errors themselves. There could be unknown scheduling problems. There could be unknown worst case execution time. Several issues exist. Design methodologies that overcome all these problems should be tested and verified thoroughly to be able to get them right. Why do we need to do so? Because several of them are safety critical in nature. And when they are safety critical, failure can be catastrophic in terms of loss of life, accidents, or loss of money that is invested. So, when it comes to models, here are simple ways of coming up with models. These pictures that you see on the left are slides taken from the book on embedded systems by Lee and Sashia. So, suppose I take an embedded processor or a chip, as you see it on this left. What is a model for it? How does a software engineer or a computer engineer look at it? He or she is going to look at the models. So, I can model a processor or a chip by its code, by an abstraction like a hardware description language, or I can model it as a hardware circuit. Such models are large, but they are finite state in the sense that they only have a finite number of different states and behaviors that they can be in, even if it is large. So we can handle them in terms of processing them, modeling them, checking them, testing them, and so on. In fact, these models, if well done, can also cater to automatic generation of code, which can in turn again be modeled by refining these models. Here is another example of model. Suppose you take a physical system like a motor or a sensor that's a part of a cyber physical system, like we saw in the quadropter. How do you model a physical system? In the real world, I can hold the physical system, I can run it and observe its behaviors. In the computing world, I model it by equations that define their behaviors as the domain, as given by the domain in which they run. Like, for example, suppose I had a physical system that looks like this in the physical world. Then in the computing world, I will work with a model of the physical system, which would be a set of equations that describes the dynamics of the physical systems. Usually, engineers from the respective domain, electrical, control, electronics, mechatronics, whatever it is, do extensive research and validation before they present the computing world engineers with the models that correspond to the physical system. Here is a third example of a model. I have a processor and then I have a physical system that I saw. We saw how the models for these two look like. Can I combine them? I had a model for this as a hardware circuit. I had a model for this as a physical component, as a set of equations. Combining them is what is cyber physical systems all about. It involves physical components from where data is collected, software or computing that is used to control these components by running algorithms, and there are embedded processes on which these softwares execute. Coming up with a model that involves all these components put together constitutes the core of modeling and design of a cyber physical system, and is obviously a very challenging act. Usually, design engineers come up with abstract models of these systems and slowly refine the model based on what is the functionality that they would like to achieve. So, in the design phase of a cyber physical system, usually, as I told you, there is no subtle difference by saying that I finished the modeling phase and I'm going to go ahead and do the design phase. It doesn't happen that way. It happens along or in parallel with the modeling phase. Here, the emphasis is on building the parts, the bits and pieces or the components that constitute the cyber physical system. I have to build a concurrent, distributed, real time system that represents the cyber physical system, and design typically involves that. Design is typically done bottom up. What do I mean by bottom up? Design involves the physical components. We've talked about them often enough by now: sensors, actuators. So I have to read the data or information from them. I have to model that data. There could be noise, a lot of issues with the data, and I have to pass on control data to the actuators. I might have to switch on or off a light bulb. I might have to run a motor that drives the unmanned aerial vehicle in a particular direction, and so on. There is a lot of embedded processes. They could be executing parallel code. If they execute parallel code, what is the memory architecture in which they run? How do I read the data that I read from the sensors and actuators? How do I present them as inputs and outputs to the computer algorithms that run in the part of the cyber physical system? Suppose there are multiple sensors reading the same data. How do I present it as one unified data? Suppose there's noise in the data that is read. How do I eliminate noise? So many things to do, right? How to balance the concurrent occurrence of physical events that are sensed with the sequential nature of the software that controls the behavior. Sensing happens almost on a continuous basis in a cyber physical system. There must be threads that run to do this sensing. How do I manage that with the algorithms that I run to do actual control of my cyber physical systems? How do I prioritize which thread runs at what time, what gives rise to what, and so on? So many challenges. All these are addressed in the design phase of a cyber physical system. Next comes the analysis phase. As I told you, many embedded systems, cyber physical systems, are safety critical in nature. By the word safety critical, please remember it means that if it fails, there can be a big loss in terms of accidents, in terms of loss of life, in terms of loss of financial resources, and so on. So, safety cannot be compromised for a cyber physical system. Because safety cannot be compromised, testing and related activities like verification, specifically formal verification, constitute an important part of the overall development of a cyber physical system. They go hand in glove with modeling and design, and analysis is an important phase towards implementation and launch of a cyber physical system. In addition to that, there are several certification standards that mandate the use of certain techniques in testing and formal verification to be able to verify a cyber physical system. For example, suppose you say that I want to launch a particular UAV. You cannot go and say, I have this cool UAV that I have developed and I'm going to launch it, start selling it in the market. we may not be able to do that. You might have to convince your stakeholders, which are most important of them are the certification bodies, that the UAV that you have come up with is safe. It satisfies all the safety parameters that are important. Get the code, the design artifacts that go into the UAV certified by these certification bodies, and then only you will be in a position to do it. So, certification bodies recommend exhaustive testing and verification to be able to cater to safety of these systems. There are several verification techniques. You can use model checking, timed and hybrid behaviors. The quadropter, that example that we saw, was developed by Professor Claire Tomelin and her group at University of California at Berkeley. They also have a lot of rigorous algorithms for formally verifying such systems and similar other systems. You can use theorem provings, which are a bag of techniques that involve a lot of mathematical notations for proving correctness requirements. There are also quantitative analysis techniques, which are constituted by what we call the real-time systems people, which includes estimating worst-case execution time, estimating power, estimating energy consumption, and so on. There are also a lot of security and vulnerability analysis that goes into these systems for verifying security and privacy properties of cyber physical systems. So, in summary, I hope all of you are clear about what an embedded system is, plain embedded system, versus how a cyber physical system works as an embedded system, and a brief of what an IoT is, their similarities and differences. For the remaining lectures in the school, you'll get to see a lot about IoT. The next lecture, we'll learn a little more about the design of embedded systems. I'll tell you about sensors, a little bit about actuators, how to read and write outputs and inputs from these sensors and actuators. How does memory look like? What is available for me for processing, scheduling, and so on. Thank you.